All right, let's dive right into this explainer. Today, we're going to uncover something a bit unsettling: why our hyper-efficient, everyday technological systems are actually secretly vulnerable to massive, catastrophic failure. You know, we live in this world that feels so completely managed by incredibly smart, dense systems. But beneath that sleek, shiny surface of automation, there's this hidden architecture of risk that you and I interact with every single day, completely, totally unaware of it. So we're going to break down exactly how these automated crashes happen, going stage by stage.
Think about it for a second. We rely on automated efficiency constantly. I mean, from the complex logistics networks that miraculously keep our grocery stores stocked to the digital grids powering our homes, our phones, and the financial markets. But I want to kick things off by asking you to imagine a pretty terrifying premise. What if a microscopic glitch, just a tiny, seemingly insignificant error, could actually threaten global stability? It sounds a lot like a Hollywood sci-fi movie, right? But as we're about to see, by really looking closely at the data and our own recent history, this isn't fiction. It's a very real, heavily documented vulnerability that's just woven right into the fabric of our modern world.
Okay, moving into part one, the threat of tiny errors.
So the absolutely crucial point to understand here is that a tiny error doesn't just isolate itself. It doesn't just sit in a corner. In a highly complex automated system, it can trigger this rapid, totally unstoppable chain reaction that threatens the whole shebang. Why? Because everything is so deeply interconnected. A single microscopic fault, say a bad line of code, a misread sensor, or even just a split-second hardware delay, it doesn't just fail and politely stop working. Since the entire system is built to react instantly and automatically, that little error gets instantly communicated to the next node, and then the next, and it just keeps compounding in speed and severity. It essentially weaponizes the system's own incredible complexity right against it.
Which brings us to section 2, the cascade of collapse.
Let's look at the exact sequence of how this goes down, from a tiny glitch to total physical and systemic collapse. It always starts quietly. Step 1, just a minor glitch. This is that tiny error we just talked about. But because these systems are so highly automated, human intervention is basically way too slow to stop what happens next. That leads right into step 2, the cascading software failure. This is where the system's logic desperately tries to correct or process the glitch, but it ends up just spreading it around, corrupting data, and confusing all the other automated responses. Before anyone can even think about pulling the plug, boom, we hit step 3. Structural and physical collapse. The digital breakdown bleeds directly into the real world, shutting down actual physical infrastructure. This whole thing goes from a quiet crawl to an absolute sprint in a matter of seconds.
All right, let's look at part 3, the snowball effect.
The underlying science in action here is just fascinating. The core mechanism is essentially this. A localized failure accelerates and it gathers destructive mass and energy exactly like a snowball rolling down a steep hill. You know how a snowball works, right? When it starts at the top of the mountain, it's small, it's harmless, you could crush it in your hand. But as gravity pulls it down the slope, it doesn't just roll. It captures more snow, which increases its mass, which then massively increases its energy and momentum. Well, in an automated system, that slope is the system's own connectivity. The failure captures more data, it grabs more servers, or takes out more grid nodes. It grows exponentially larger and faster until it is quite literally an unstoppable avalanche.
Let me give you a real and, honestly, a pretty dark example of this. We are looking at a shocking historical contrast where a literal fake nuclear attack tape loaded purely by accident almost started World War III. This is the ultimate, terrifying example of a tiny error acting like our snowball. Over at NORAD, which is obviously a deeply complex, absolutely vital defense system, someone accidentally loaded a single training tape, well, a simulation tape, that showed a fake incoming nuclear attack. Because NORAD was completely designed for rapid, automated escalation in response to threats, that one fake data point immediately triggered a massive high-stakes chain reaction. A localized, totally harmless training exercise rapidly gathered momentum through the entire defense network and brought the world to the absolute brink of global annihilation.
But we don't have to look at the Cold War to see this. Bringing it right into the modern digital age, we see the exact same runaway loop happening all the time during a DDoS attack. In this case, superfluous files act as the snowball that completely overloads a network. See, a distributed denial of service attack doesn't usually rely on one massive, super complex virus. Nope. Instead, it relies on a massive flood of tiny, seemingly totally harmless, pointless files or data requests. On their own, individually, they are absolutely nothing. But when they are poured into a highly connected system, they gather mass. the system tries to process them, utilizing its own automated efficiency to neatly categorize and route all this data, until that very efficiency causes it to entirely overload and collapse. The system's own architectural brilliance actually facilitates its own destruction.
And that sets us up perfectly for our final point, Section 4, the efficiency paradox. We really need to completely reframe how we view these system crashes. They are not just random bad luck. They are runaway positive feedback loops, perfectly engineered by the system's own hyper-connected design. Think about it. When a major system goes down today, we always tend to call it a freak accident or an unforeseen glitch. But the source material for this explainer makes a really vital argument. These are absolutely not accidents. A positive feedback loop is a process where the output of a system actually amplifies the input, causing it to just grow and grow and grow. Because we build our digital networks to automatically react and share data instantly, we are literally engineering the exact perfect conditions for these runaway feedback loops to thrive. The disaster is baked right into the blueprint.
And this matters to all of us because the very efficiency we constantly demand from our high-density systems is exactly what guarantees their extreme fragility. We all want high-density efficiency, right? We want systems with zero delays, absolutely no friction, and no wasted space or time. But to get that kind of perfection, we have to strip out the buffers. We remove the manual human check-ins, we take down the isolation barriers, and we eliminate the friction that used to stop that snowball from rolling down the hill in the first place. By maximizing efficiency, we are actively stripping away resilience. It is a one-to-one direct trade-off. The tighter, the faster, the more seamless the system gets, the more incredibly fragile it becomes to that one single microscopic error. So, I'm going to leave you with this final thought to ponder. Think about the razor's edge that our modern world balances on every single day, and wonder when that next microscopic glitch is going to spark a runaway loop. We are constantly, obsessively pushing for more automation, faster response times, and deeper, more complex connectivity. But as we've seen throughout this explainer, every single step we take toward perfect efficiency is simultaneously a step toward ultimate fragility. So the question really isn't whether another tiny error is going to happen in our vital systems. We know it will. The real question is, when it does happen, are we going to have any buffers left to stop the avalanche? Thanks so much for exploring this with me today, and definitely keep questioning the systems around you.